Okay, just give it another 10 seconds. And in that time, I will just get my screen up. Good afternoon, ladies and gentlemen. Once again, my name is Shafir. I represent the ecosystem development team at the Sharjah Research and Technology Innovation Park. I would like to very quickly go over the activities that we do here at the park before we kick off to our webinar today, covering desalination technologies. If I can find a way to switch the screen, there you go. The Sharjah Research and Technology Innovation Park was established back in 2016 by His Highness Sheikh Dr. Sultan bin Mohammed Al Qasimi, that is the ruler of Sharjah, and with a core mandate to rapidly commercialize the research and development that comes out of the American University of Sharjah and the University City of Sharjah. So we're actually located adjacent to some of the top level academics. After the establishment in 2016, we actually came out of stealth mode in 2018, which actually introduced us to the first set of companies who established here with us, different levels of startups and SMEs that have been associated with us. We actually moved into our brand new HQ just about 6 months ago. And we're proud to say that we have already onboarded several innovative entities to the tune of over 100 at this point. The park actually focuses on six deep tech segments. That includes water technology, environment technology and the circular economy, renewable energy, healthcare technologies, including digitization, mobility, logistics, and smart cities, and finally, production, design, and architecture. So we're talking about roughly close to $1 trillion cross segment that the park covers. The mode that the park actually operates has a very unique approach, which we like to call a triple helix approach. So this model of technology transfer actually engages us with the government, the academia, the business sectors, and really we develop this interactive environment for all these different stakeholders to come together in the development of innovative technologies. Just to give an example, I could probably talk about one of our startups that are based in the park, which happens to be involved in several sectors of artificial intelligence. We actually identified specific government entities in the Emirate of Sharjah to the tune of 15, where we did, along with this startup, had a AI assessment program, and now we're helping them to develop specific case studies and data maturity models for these government entities to actually utilize AI-assisted decision-making. And of course, our close proximity with the University City gets the academics on board in supporting these initiatives. And one of the main purposes of the park is actually to help these businesses thrive in the region, have this new technologies come in from the international markets, develop new technologies from the universities and the research and development, and have a pilot, an open innovation pilot program for them to actually test in a sandbox environment. Proud to say that at this point, we have over 100 entities established here with us. We are projected to have approximately 250, so we're looking to more than double the number of smart tech companies by the end of 2021. Despite COVID, I think that's a very bold claim. We have already had over $100 million invested in the Sharjah Research and Technology Innovation ecosystem since 2019. Despite all the difficulties across 2020, it's a proud statement for us. We have already implemented 6 anchor deep tech pilot projects across 2019 alone. This includes projects across photovoltaics, agri-tech, 3D construction, additive manufacturing, AR, VR, and mass transport innovation as well. And as I mentioned, we have the unique opportunity of being located right next to University City. So we've attracted over 20,000 visits across 2019, and we almost doubled that virtually, of course, in 2020. Having access to over 22 universities that includes 2,000 PhD holders across the 2.5 square kilometer radius. I think this is the highest concentration of PhD holders and academics. I would possibly assume across the Middle East. Another key jewel in Sharjah Research Technology and Innovation Park crown is the soil lab, which we have just inaugurated. Obviously, the first 2 floors have already been completed, and this is going to be, once concluded, would be 3 floors of different types of equipment available to all types of entrepreneurs for rapid prototyping, your 3D printing of different materials, including plastics, polymers, metals, so on and so forth, and other equipment such as your CNC machines, laser cutting for wood, textiles, and so on. So really a one-stop shop with a gym membership sort of program for these entrepreneurs to have access to such equipment and to create, to bring reality to their innovation and ideas. Another key aspect is the Sharjah Angel Investment for development program that we have initiated in December. This was actually a soft launch that we conducted in December, and the response and the interest has been phenomenal. Where we were in just 2 informal sessions, we were able to get 2 of our startups a significant amount of investments from our angel investor group, which has led us to actually formally introduce this network. And we will be conducting investment programs across different segments for our startups. Without further ado, I would like to introduce our panelists for today. First, we have with us Mahesh Madriwar, I hope I pronounced that correctly, who is currently the Proposal and Estimation Manager for Desalination at Aquatech. Mahesh is a chemical engineer with over 20 plus years of experience in water, wastewater desalination as an O&M engineer. He has been involved as a commission engineer. He's a process engineer and process and proposal manager. And with over 20 years of experience, I thank Mahesh to this opportunity to be a part of our panel today. Our second panelist today is Carlos Tuhan Alvarez, who is the product manager for Filterlight Iberia at Saint-Gobain, an industrial engineer and master in water engineering and project management. He has over 12 years of experience in projects related with water engineering and technology. Carlos Tuhan has working experience in several companies and organizations, both in the private and public sector. That includes Saint-Gobain, Traxa, FAO. He's been involved in several geographical areas across Latin America, Africa, and Europe. Of course, this has allowed him to develop a strong component of implementing innovative solutions for water treatment based on a CapEx and OpEx reduced approach. And of course, currently he's responsible for Filterlight product development at Saint-Gobain and is responsible for Spanish-speaking markets and accounts. I would like to open the floor to Mahesh first to do a quick intro before I move on to Carlos. Mahesh, the floor is yours.
Thank you, Shifu. Good afternoon, everybody. My name is Mahesh, and I will be talking about the reliance on chemical in desalination industry. I will start sharing the screen, Shifu, if you don't have a problem. Hello? Can I start sharing the screen?
Yeah, please, yeah.
Okay.
I think that should go up now, yeah. Sometimes we tend to have
yes. Just a minute, give me 1 minute.
Sure.
Yeah. Can you see my screen?
Yes, perfect.
Yes. Basically, seawater reverse osmosis process, if you will see, it is divided into three portions: pre-treatment, which consists of clarification and sedimentation process, then filtration process, then basic membrane separation process for reverse osmosis, and post-treatment for remineralization or further polishing of seawater permeate.
Mahesh, if you could, sorry to interrupt, if you could just hit the view slideshow so we can see the screen a bit larger on your PowerPoint.
Sorry. Yes.
Perfect.
Yeah. So as I explained, seawater reverse osmosis system is divided into three portions: pre-treatment, which consists of clarification, sedimentation, filtration. There are two types of filtration: media filtration or ultrafiltration. Then basic main membrane separation process or reverse osmosis process. And then post-treatment, which may consist of further step of reverse osmosis process and remineralization by using lime and carbon dioxide. These are the chemicals which are used in desalination system. In clarification system, we use ferric chloride, polyelectrolyte, and acid. Acid is required for RO, means to avoid fouling in RO, but that is by choice. And then chlorine gas or sodium hypochlorite or hypochlorite generated at site for biofouling prevention. Media filtration and ultrafiltration both may require ferric chloride as a continuous dosing, but that depends upon site to site. Then seawater reverse osmosis system, it requires basically four types of chemicals: antiscalum, sodium bisulfite, sodium hydroxide. In some cases, when boron requirement comes in picture, then we may require to add sodium hydroxide in the reverse osmosis system. Then acid, means of course when we are we want to add sodium hydroxide, we will not be adding acid. It is one of the hydroxide and acid. And low pressure RO membrane, again the same chemicals may get used. The basic and remineralization process is the third step of desalination industry, where we use sodium hydroxide to stabilize the pH of produced water, chlorine gas to avoid further biofouling into the pipeline and distribution system, limestone and carbon dioxide to do remineralization or to boost up the LSI to avoid corrosion in piping system and distribution system. So these chemicals are basically used on continuous basis or regular this one. Intermittent chemical used are on two types: on ultrafiltration system for cleaning and for ROCIP for cleaning. These are all cleaning chemicals like sodium hydroxide, acid, and sodium hypochlorite are used in ultrafiltration system. And citric acid, sodium hydroxide, SLSS, EDTA, and STPP are used in ROCIP. Another thing is continuous chemicals. It is difficult to replace them as they are required as a part of process. But one of the area where we can replace them or avoid them is intermittent chemicals. In continuous chemicals, if we'll see, all these chemicals are required to reduce either footprint of the plant or as a process requirement. Like for ferric chloride and polyelectrolyte, if we will not use these chemicals, then we may not able to form the flocks and settle them faster. So we may require to provide a higher surface area to settle out the particles present in water. So that's why basic chemical consumption, which can be optimized or reduced or eliminated, is the chemical cleaning chemicals in UF and RO, which are more hazardous and harmful also. So for for reduction of these chemicals, there are two methods. This is the normal RO CIP process, where we prepare these chemicals in the CIP system and pump into RO membranes through this. And again, it is collected back. It is collected back into ROCIP system. So this process is continued for 3-4 hours so that all these foulants are removed. Without using chemicals, there is another novel cleaning method which is nowadays used in lots of plants and which are showing a good amount of success rates with respect to chemical cleaning. This is called as osmotic cleaning. In osmotic cleaning, this is normal operation cycle. Service water comes, it feeds water, means feeds into RO membranes. Permeate is collected, and then from permeate it is going to permeators. These are all permeators. From permeators it goes to permeate tank. In osmotic cleaning, we, instead of making the chemical cleaning water in the CIP tank, we use RO reject water. From RO reject water is fed into RO membranes. From permeators, permeate will come back, osmotic gradients is created, and all these foulants will get disturbed and will be flushed through flushed from RO membranes. So in this method, we are not using any chemicals and avoiding complete uses of ROCIP chemicals, which are more hazardous and more problematic to handle. This is general osmotic cleaning mechanical GA, like these are RO pressure tubes and these are permeators which are getting connected to the RO membrane system. This is a front view of that RO osmotic cleaning. So basically, this is one of the innovative method to avoid ROCIP chemicals. That way we can reduce the dependency on chemical in ROCIP chemicals.
Thank you very much, Mahesh, for that insight. I'm getting some questions coming in, but I will leave that towards the end of the webinar when we have our Q&A session. So I would like to pass on the virtual microphone to our second panelist for the day, Carlos. And I believe Carlos has a presentation as well, so if you can just try the share screen.
Yeah, I'm sharing the screen with you. Yeah. I don't know if you can you see my screen?
Yep, perfect. Yeah, just if you can hit the
okay, that's fine.
Play slideshow. Yeah, perfect.
Okay, so first of all, many thanks for the invitation and for this so interesting webinar. So my idea is to do a brief presentation about Filterlight, which is a filter media used in the pretreatment of desalination. And as you will see, we are really aligned with the idea of reducing the reliance on the chemical usage of, especially for the pretreatment phase and also afterwards, because we reduce the chemical consumption, because we improve, Filterlight is able to improve quality, and also it's able to save energy and water coming from backwashing. So the idea is to give a broad view about the product and about their application in the pretreatment of desalination. So first, who we are. I belong to Saint-Gobain, which is a big multinational group. Filterlight is the filter media brand used for filtration in different applications: desalination pretreatment, water purification, urban wastewater, industrial purposes. Saint-Gobain is devoted to individual and collective solutions for well-being, and in our DNA is the innovations. We are a company with 350 years old, and we are still alive, and we are still proposing new things, and we are so big because we really believe in innovation, and Filterlight is an example of this innovation philosophy. Three highlights about what is Filterlight and what can bring Filterlight. It's a filter media able to save in operational cost more than 50% on the filtration step. It allows to design filtration rates more than 30% than conventional filtration systems. And we think that is the more deepest change that can be done in a desalination plant without civil works. So it means that only in 3 years, all the investment is returned, and the change in terms of energy, in terms of production, it's so high that it's difficult to do something more revolutionary in a desalination plant only by changing the filter media. I will talk about 3 topics. First, a short introduction about existing filter media and their limitations. I will introduce Filterlight, their properties and technical specifications. And finally, I will explain what it brings in desalination pretreatment. First, As you well know, it's something that it was mentioned in the previous presentation. The pretreatment is a key issue in a desalination plant. We need to protect the reverse osmosis. There are many different steps that can be done, or many different technologies, but it's clear that filtration is one of the main technologies and the more reliable technologies that can be set in a desalination plant. The granular filtration, that is a very well-known technology, helps to reduce the levels of SDI, TOC, suspended solids, retaining particles, and improving the quantity of TOC dissolved in the water. The purpose of the pretreatment is to handle with bad quality water, guarantee good quality to the reverse osmosis, and trying to have operational and maintenance affordable costs, which is sometimes very difficult if we have a very bad quality inlet. And trying to guarantee the production, we need to provide enough water to the reverse osmosis, otherwise we have to stop some frames of the reverse osmosis. The typical approach for filtration is to use sand, but sand is a non-porous material, so it has the limitation of working with very low filtration rates, or otherwise it becomes clogged very fast, or the head loss is so high that we are forced to backwash it in a very frequent way. Also, the relation between height that we can install, the height of the layer and the effective diameter, should be below one specific number, because otherwise also the head loss is so high that it's not possible to operate this kind of filter. It's expensive in terms of operation and maintenance because the frequent backwashing, and also is low, the efficiency is low when we have bad quality. In order to solve those kind of problems with sand, the typical approach is to set on top of sand anthracite or pumice material. Why? Because they are porous material and they have longer or bigger specific surface, so they can retain more suspended solids without clogging. And we can combine sand and anthracite or pumice in order to have longer filter runs, to increase the quality, because it's possible to build up height layers, and this is initially the idea, but the porous materials, they have some limitations. They are weak materials, their resistance is low, and when they are combined with sand during the backwashing, they become fastly run out, because the contact with between sand and anthracite or pumice is very aggressive. Sand is much harder in terms of hardness in the Mohs scale or attrition hardness. So the sand gets the erosion of the anthracite and pumice, and after 3, 4, 5 years of operation, the anthracite or the pumice is completely run out, completely flushed away from the filter, and it needs to be replaced. So what is Filterlight? I am going to come into the material properties and about what we have and what we are able to do. Filterlight is a ceramic material, an industrial material. It's an expanded clay. We take clay from a quarry, and this clay is expanded in a rotary kiln at 1,200 degrees. And we managed to burn all the organic matter that contains the clay. So all this space is taken by porous, and we have an huge, massive porosity in the material with an enormous specific surface, and a specific surface bigger than 1,500 square meters per cubic meter. So in a few words, what we have is a huge warehouse for storage suspended solids coming in the water. The material has a high resistance and a long durability. In terms of hardness, is close to sand. So the combination with sand is perfectly possible, and the duration is much longer than other porous material. And we are able, because it's an industrial process, we are able to produce three different types of density, which allows us to have tailor-made solutions depending on the water to be treated. This is a little bit how it looks like, Filterlight. It's a granular black material, and the picture on the right is the porosity, the pores of the material. There are many pores which are conductive, so the water goes through the pores. The suspended solids are retained on the surface of the material, and the head loss is extremely low, and the filter runs of the filter are very, very, very long also. So we have a very low operational cost. This is a comparison in 4 pictures, 80 times extended between 2 types of Filterlight, high density and normal density of Filterlight against sun and anthracite. What we can see is that the porosity, the shape of the surface, the material characteristics are completely different. And this is the explanation of the different properties in terms of quality filtration and hydraulical performance. Filterlight is not new. We have been treating water since 20 years ago. It's a Nordic product produced in Norway, and we have many references all around the world in drinking water, but also in desalination. We start to have some important reference since 10 years ago. And it's a proven product and used by many, many companies. And the idea is to gain some space in Middle East, because we are convinced that the product can be a nice solution, a perfect solution for improve the performance and designing of the desalination plants in the area. There are 2 ways of designing with Filterlight for treating drinking or desalination water. The first is the first branch, which is the more common one and is related with the replace of sand, is devoted to particulated filtration, to physical filtration, so removal of suspended solids, TOC, SDI improvement. The idea is to replace sand and anthracite, sand and pumice or sand, and the approach is to get lower OPEX, to deal with peaks of suspended solids and algae blooms, to increase the filtration rates, and to guarantee a better quality. There is a second approach that changing the process or changing a little bit the way of designing, we can carry out bioprocess or chemical process in order to remove ammonia, nitrates, arsenic, iron, manganese, replacing intensive technologies and reducing CapEx and OpEx. But in this presentation, we will keep focus on the branch number 1, which is the one that is related with the sand and anthracite replacement. And finally, what we bring in the desalination, the way of designing with Filterlight in granular filtration, we have two approaches. One is the monolayer. We can set only one type of Filterlight. Normally, we choose for the desalination the MC0.8 1.6 material, or we can do something that other filter medias cannot do, which is to combine 2 types of porous material. Why? Because we are able to produce porous material with different densities. We can put 2 types of Filterlight, one with low density, the material NC 0.8, 1.6 on the upper part, because we are able to produce a very low density material. And we put in the down part a material with high density, the HC 0.51. Those materials have a very differentiated settle velocities, so there is an intermediate in between. So we have 2 porous material working in series, with advantage of having porous material working in series, long filter runs, very good quality. That's a little bit the approach. And also the relation between both materials, because their resistance in terms of hardness is more or less the same. It's very good. They're materials that the one does not run out the other. So the duration of the total solution is about 15 years. We don't have the typical problem of the porous material combined with sand. Also, it's possible to combine Filterlight with sand, replacing anthracite, and the lifespan is much longer and the properties are better. So in order to demonstrate that we have longer filter runs, we save water, we save energy, we save chemicals, we did a test in the lab research of Suez in Paris in order to see what is the hydraulical performance of Filterlight regarding sand and anthracite and sand. And we treat 2 types of water, one water with low levels of turbidity, a turbidity of 2 NTUs. And what we get is that our material has longer filter runs than sand and anthracite, 1.5 longer and 2 times longer than sand. And when the water gets worse in quality, when we take water directly from the river with any coagulation, flocculation, sedimentation, this duration of filter runs, this difference between sand and anthracite increases, because the worse the quality, the higher the difference between other porous material. And this makes a lot of sense, because we offer a better performance when the water quality is worse. That is what is the moment that is more necessary to have a better performance. Also, we test Filterlight with two filtration rates, a filtration rate of 8 meters hour and a filtration rate of 15 meters hour. And what we verify is that we were able to filter the same cubics per square meter, doubling the velocity for the conventional filter media. When you increase the filter rate, the total volume that the filters are able to treat, it's much lower, because normally they work in surface and they don't work in the whole volume as Filterlight does. Also, talking about quality and chemical reduction dosage, we test Filterlight against sand and anthracite in order to see the power in TOC removal. And what we find is that at 5 meters hour, we were able to remove the 50% of the TOC, when anthracite sand was able to remove the 37. And for 15 meters hour, we were able to remove 40, and sand and anthracite only 26. And the relative distance between both media increases when the high rate of the filtration rate increases. And as final slide, talking about the SDI, we did a long test, a full-scale test in the desalination plant of Alicante in Spain. And what we verify is that the average value of SDI of the water treated with Filterlight, the blue line, regarding a filter with sand 0.5 millimeters, which maybe is the best quality that you can get. It's there is an average distance difference of 0.3 points of SDI, which is even higher when the water inlet quality gets worse. It goes up to 0.8, 1 point of SDI. That, in terms of saving chemicals, cartridge filters, it's really has a very big impact. And summarizing everything, we can say that in CapEx reduction, Filterlight in a big plant, we can save we can increase the filtration rate in a 30%. So imagine this, what can it means in a big desalination plant, in a new design. We can save a lot of new filters. We can do a filtration step smaller with a smaller investment and with a smaller footprint. Also, we can, for existing plants, we can increase the capacity of the filtration step without only by replacing sand, and because we can work a high filtration rate. And in operational reduction, we are able to increase the filter runs between 50 and 150%, reducing with a reduction of the ripening time, and improving the SDI, the suspended solids. Our estimation is that in a desalination plant of 1 cubic meter per second, we're able to save $500,000 per year, talking in euros. So we are able to produce more water with better quality and with a lower cost. And I keep, that's all. Many thanks, and I keep available for your questions. So many thanks.
Thank you very much, Carlos and Mahesh, for your insights. I have a few questions coming in. First question is for Carlos. I guess it's specific to your, just to open that up, yeah. It's just specific to your product. How easy is it for this system to be retrofitted for existing filtration processes? I'm not a technical person, but I guess the question is relevant.
It's relevant. It's very relevant. It's so easy that all the work that should be done is just empty the filter that is full with sand and install Filterlight. There is not needs for retrofitting the backwash system. There is no needs for retrofit any other device, or it's only a change of filter media. So it's so easy like this. There is any mystery.
Okay, all right. There's a general question for both our panelists. their needs for desalination has continued to increase. The population is increasing. One second, I just closed the window just a second. Yeah. And the requirements have been going higher. What can we do to continue to reduce the energy requirements? Because there's always an impact on the environment for our water needs. I would leave that open to the floor. Probably we can start with Carlos and then go to Mahesh.
Mm-hmm. For sure. For me, there are clearly two approaches. One is to increase all related with the efficiency in the pretreatment, with all the steps, not only filtration, which is important, as we have said with Filterlight, we improve, we can reduce remarkable the consumption in backwashing, for example, but all the steps should be tuned somehow, the DAF, the set tanks, but especially with this more demanding is the reverse osmosis, new materials, new pumps, new approaches, new way of operating them should reduce those consumptions that are really for the moment high, but they are being reducing. Maybe Maes has more to say about this topic than. Mm-hmm.
Sure.
Yes, I think it is a very interesting topic and a very huge on discussion point of view. I will just give you a brief. Energy consumption in desalination plant not long ago was around 4.5 to 5 kilowatt hour per meter cube. Then it started decreasing, and now it has come down up to 3.1 kilowatt hour per meter cube. And what we are thinking that it is going to come down to 2.7 kilowatt hour per meter cube in near future. In desalination industry, one of the biggest consumer of this energy is a reverse osmosis system. Around 60 to 70% of total energy is get consumed in reverse osmosis. So major innovations are going on. Major innovations are required on RO membranes, which will consume less energy and produce more quality.
Thank you very much, Mahesh. We have again another question for both our panelists. A high amount of desalinated water is now being used for general consumption. And we know that one of the chemicals found in seawater is boron. What can we do to reduce? What can we do to reduce the amount of boron in the desalinated water, and how soon can we be realistically utilizing more seawater for regular consumption? I think it's related to using desalinated water for drinking purposes. This is what,
yes.
what I understand. Yeah.
Can I chip in?
Yeah, please. Yeah,
Yes.
It's open to both hands.
Yes, I understand boron as per WHO guidelines for drinking water. The requirement of boron is 2.4 ppm. But again, it is different for different countries. Like in Middle East, we accept up to 2.4 or 2 ppm of boron. In Singapore, it is required, it is less than 0.5 ppm of boron. So basically, this is a process driven. Reverse osmosis itself is able to remove the boron. The normal concentration of boron in seawater is around 4.5 to 5 ppm. And 50% reduction is quite achievable. The challenge comes when it is a stringent requirement like in Singapore, when we required to reduce boron to 0.5 ppm. Then we, as I had mentioned in my chemical presentation also, that we may require to increase pH of seawater to increase the rejection of boron across RO membrane. So as of now, the technology is provide second stage of reverse osmosis system and increase pH of this product, pH of RO permeate to the level of 10 and avail the benefit of rejection of membrane at boron at higher pH across membrane. So this is a technology and very much achieved worldwide on that.
Yeah, in some cases when the level is very high, to use 2 steps of reverse osmosis. This is very common. I think that there is still a research line related with absorption of the remaining borers when, as last step in the remineralization step, also can be added an absorption process in order to remove the boron left. It can be something that is, we have been researching in this line, and I think that something is doable in this line, but for the moment it's the reverse osmosis who should remove the boron, and it's perfectly doable, but it's expensive. It's expensive because sometimes you need 2 steps of reverse osmosis, and is demanding in energy or pH adjustment, as Mahesh has commented. Yeah.
Perfect. Thank you, Mahesh and Carlos. We have another question. Okay, with the announcement of Abu Dhabi again launching one of the largest desalination plants in the region yet again, is there an alternative method to having larger and larger desalination plants, or is it better would decentralized desalination plants make more sense from energy consumption environment perspective? I again leave that open to the floor.
Yeah, again, as a system integrator, I can pitch in for this solution. See, when it is a decentralized, definitely energy consumption will be a little bit more on that front. When you have, like what the questioner had asked for, when it is a centralized desalination, if you will see Abu Dhabi, this contract, it is very cheap. The previous means when it is started, the basic desalination for drinking water is on boot purpose. The few years ago, the cost of this boot was around $1, $1.5 per meter cube, per 1,000 liter. Now it has reduced around $0.2, $0.3 per meter cube. The Abu Dhabi one, I think it is around $0.25 or $0.3 per meter cube because of the solar energy requirements and captive power plants and all these things. So definitely when it becomes centralized larger plant, energy consumption also reduces, financing models are, all these things changes, and we get it at reduced cost also. So again, it depends upon, if suppose it is a centralized and transmission is 100 and 150 kilometer, which is not viable solution, at that time it is a problem. Then we require decentralized desalination process. Like in India right now, Gujarat government has 5 desalination plant at different 5 locations instead of having one at one location. So it depends upon the geography and requirements on the desalinated water.
Interesting. I'm not sure, Carlos, if you'd like to add any comments.
Yeah, fully agree with my approach. No, the larger the plant, the lower the cost in terms of energy investment. The cubic meter is cheaper, but that's true that if you have a very long supply in terms of distance, you need to repump the water, and this can be a problem also, or a challenge. So a balance should be needed. And it's very depending about how the distribution of the water should be done afterwards. But the centralized approach makes a lot of sense for big populations that you have in Abu Dhabi. Yeah.
Thank you, Carlos. We have another, I would say, a general question. Yeah, we all know that the okay, I think it's. Yeah, we all know the byproducts of desalination results in several harmful byproducts. What can the desalination plant themselves do to reduce such chemicals? I'm not sure if either Mahesh or Carlos. I think it's more about what we can do with the byproducts of desalination. Can they be? I think it's more about, are they being pumped back into the sea? So on. What can we do about these harmful chemical byproducts as a result of desalination? Is there more we can do to support the environment? I think that's where this question wants to go.
For every desalination plant, environmental impact assessment study is conducted. So basic requirement of environment impact assessment is which chemicals we are going to use, how these chemicals are harmful for seawater, seawater living organisms, and or for human consumption. All these studies are conducted. The chemicals which we have shown, these are not generally carried to the sea. The brine water means, or they are added in parts per milligram, means hardly 4 or 5 gram per meter cube per 1,000 liter, which is of very less quantity. Yes, we understand it is an impact, and generally we try to avoid as much of as chemicals are getting used into desalination industry. But before finalization of any desalination plant, the EIA studies are conducted and eliminated all these nuisance which will be which gets created due to these chemicals.
Okay, thank you. Any comments from you, Carlos?
No, I agree with Maes.
Okay, we have a bit of a technical question. What are the design considerations that you would take into account for high flow rate cartridge filtration applications? Again, I'm not a technical person, so I'm not sure. Maybe either of you would like to.
So the question is, how are the considerations for designing?
What are the design considerations when you take into account high flow rate cartridge filtration applications?
Yeah. Okay. But it's if you are designing a high rate and you're using cartridge filters, that more or less is mandatory to set them before the reverse osmosis as protection. You have to take into account the quality that you will get in those cartridge filters in terms of solids and in terms of the size of the average size of the solids. For installing cartridge filters, you have to choose the size of the hole, the size of and there is several sizes between 5 microns and 20 microns. So the better the quality, the smallest that you can choose the hole. And you can really have to know very well your water and your pretreatment in order to make a good choice in terms of the size of the holes for the cartridge. Otherwise, you will replace them in a very frequent way. So it's very important to do a proper pretreatment before their cartridge filters.
Thank you, Carlos. Mahesh, if you have anything to add.
Yeah, no, I think Carlos has answered properly on this.
Okay, thank you very much. I'll just, we have 2 more questions. I have to switch between windows. Just give me 1 second. There are several challenges for algae bloom. I guess that's algae blooms. How can we ensure reliable operations when we have this phenomena? Mahesh or Carlos?
Yeah, this this phenomena should be approached with a very, very, very accurate and good pretreatment. It should be chosen the right technology. Normally, DAF technology has a very good performance with algae, but also a good filtration step. And in this case, I should mention Filterlight. The material has very special properties for algae removal. Was tested in deep by Thames Water, the company that runs the London water, because they have algae problems in a desalination plant that they have. And it was demonstrated that the relation and the capacity removal for algae is very good, but algae should be addressed in the pretreatment, because for sure the reverse osmosis will remove the algae, but if the reverse osmosis removes the algae, you will spoil in a very fast way the reverse osmosis. And this is not the purpose. No, the purpose is to remove all of them before the reverse osmosis. So the pretreatment is the key issue here.
Thanks, Carlos. Maybe Mahesh would like to add something into it, or?
Yes, that's exactly this. For algae, the pretreatment is a key. Like what Carlos said, that presently everywhere, if we'll see we use DAF technology, which is supposed to take care for this algae bloom, and then a good filtration media is a second line of defense from algae. Yes, algae can be removed, but it must not get carried away up to reverse osmosis system. Otherwise, we will not able to run the plant for longer duration.
Okay, we have one more question. Any comments on integrated carbon capture and utilization with reverse osmosis seawater desalination? I'll just repeat the question again. Any comments on integrated carbon capture and utilization with reverse osmosis? So I guess it's to reduce the carbon footprint of the desal plant, if I'm not mistaken. Maybe Carlos, if you'd like to.
In our case, we have implemented a calculation tool for assessing all the savings in terms of energy and water, which are translated into CO2 reductions, in order to see how much CO2 we are able to save in a desalination plant, also in a drinking water treatment plant. And it's very remarkable the impact that the filtration step has in this CO2 reduction. For sure, the reverse osmosis is the main component in terms of energy supply in a desalination plant. So an improvement in the reverse osmosis membranes, materials, or energy process will save much more CO2. But in the filtration step, we can do something about CO2 reduction in a remarkable way. Yeah.
Thank you, Carlos. Yeah, if you'd like to. If Mahesh, if you'd like to maybe add some comments to that before we take some closing remarks from both our panelists today.
No, thank you.
Okay, so before we close, maybe a few comments from Carlos and Mahesh before we close the webinar. Any final thoughts, future expectations, where you'd like to see the role of innovation in desalination? Probably. I guess if anything is to go by the last 1 year, we really cannot anticipate what the next couple of years would hold for us. But what would you like to see in the space of desalination, both from a consumption perspective and from an environment perspective? Probably we'll start with Carlos, and then we can have a few words in from Mahesh.
Okay, and this is really what is happening in desalination is really such interesting a scenario, because as Maes has mentioned, the reduction of the cost, the production cost of the cubic meter in the last 10 years has been amazing, unbelievable, and there is still room for improvement. I will say in every single step of the treatment, there is still many improvements that can be done in materials, process designing, technologies, combination of technologies. I think that we have still 5-10 years of really big improvements, and we expect to have a cheapest cubic meter in some years, and especially a low demanding process in terms of energy. So I think that we have very interesting 5 years in front of us, and it will be very interested to see what is going to happen.
Thank you very much, Carlos. Mahesh, any few closing words?
Yeah, thank you first of all for inviting us here. But the challenges in front of our desalination industry are for reducing energy consumption, and then reducing the wastage generated in desalination plant, and the reliability in terms of producing quantity and quality of the desalinated water. The constant innovations are happening. The basic innovation required is energy consumption and chemical consumption. And I hope that in next 2 or 3 years, we may see some big breakthroughs happening in that front.
Thank you very much, Mahesh. I would like to take this opportunity to thank both Carlos as well as Mahesh taking time outside from your very busy schedules to be a part of this webinar at SRTIP. I hope we can continue to collaborate, hopefully in the near future, especially in this space. It's a very big space for us here in the Middle East. And I'd like to thank all our viewers for connecting and joining with us today. In conclusion, thanks once again to our panelists, and look forward to the next couple of webinars. Thanks very much, and have a great day.
Thank you.